Since 1986, there has been the development of a test or experimental vertical axis wind turbine called the EOC, which had a capacity of 4 megawatts. And since then, production of large-scale vertical axis wind turbines has ceased, or there is not much evidence. In this video, we are going to be looking at the benefits of vertical axis wind turbines, and we'll compare it briefly with horizontal axis wind turbines to see how viable this option is in our current technology. So in this video, we are going to be taking an introduction into large-scale VAWTs, objectives for VAWTs, types of VAWTs, benefits of VAWT over HOT, major disadvantages of VAWT, typical material for VAWTs, performance comparison in a wind farm. First of all, several experiments have been ongoing for vertical axis wind turbines. Although in current day professional world and environment, we mostly see horizontal axis wind turbines. But vertical axis wind turbines have existed for a very long time. When it was used for grinding, VAWTs have been used for a very long time. Probably due to challenges with scaling up of these wind turbine systems has led to a drawback in its implementation. So in 1986, we had a 4 megawatt wind turbine, a VAWT was developed and tested called the EOC. It was not until 2002 where we had an actual 4 megawatts or more horizontal axis wind turbine. So we see that vertical axis wind turbines have been developed long before horizontal axis wind turbines. The reason for this slow pace in technology development is a subject for further discussion. However, in this video, we are going to look at how we can use QBlade for the design. So this is just a preliminary into the use of QBlade for wind turbine system or vertical axis wind turbines. So the vertical axis wind turbine, the EOC, was a Darius type of wind turbine. So it had a height of 96 meters and diameter of 64 meters. In present day market, a horizontal axis wind turbine with a capacity of 4 megawatts has a height of 124 meters and a diameter of 112 meters. We see right here that horizontal axis wind turbines are much larger in size compared to vertical axis wind turbines, of which they are of the same capacity. So it doesn't matter whether the airfoils for vertical axis wind turbines only can harness between 10% and 40% of the wind, because apart from what is being harnessed directly from the wind, you also have turbulence wind that is creating an effect on the wind turbine. So in effect, the wind turbine can actually run faster than the wind speed, or it can rotate faster than the wind speed. So there's a question with the sizing of VAWTs compared to HOT. So just like I said earlier, for the different VAWTs, you have from 10% to 40%. So it could either be from the Savonius to the Darius or to hybrid systems for which this efficiency exists. And for HOT, you have 59.3%, which is based on Bette's law. So presently, the goal for experts is for them to achieve a similar capacity for VAWTs compared to HOTs, in which case they need to spend less money to achieve this. So it needs to cost less before it to become viable as an option. Whether that is already achievable is yet to be established. However, that is the goal. So I say in which case the efficiency of the vertical axis wind turbine in extracting only 10% to 40% will not really matter, because you already have the capacity of your system at its rated value. So for vertical axis wind turbines, you have the drag driven, the lift driven, and the hybrid types. So for the drag driven, you have the Savonius, which can be modified into the spiral bladed and the helical bladed. For the lift driven, you have the Darius, which could be, other options could be the straight bladed, the Geromil, the H rotor, or the 4 rotor. So in this image, you can see a Darius VAWT, which is like a 3-bladed or 3-rotor straight bladed vertical axis wind turbine. Then you have the hybrid Darius and Savonius self-starting wind turbine. So benefits for VAWT over HOT is that there is no need for a yaw system. In other words, there is no need for a mechanism that will be twisting the head of the wind turbine system to face the direction of the wind. For a vertical axis wind turbine, you don't need that. So capability of blades running above wind speed. So for example, aside the direct wind height that is impinging on the airfoil or the cross section of the blades, You also have the effect of this wind after it bounces off the blade or cross section. There's an effect of wind on the blade itself, and also the turbulence that is created on the boundaries surrounding those blades. Are several ways that wind effects can ensure that the blades run faster than the wind speed of the environment. That's when you take into consideration the tip speed ratio. So the blades can usually be made by mass production extrusion when a twist is not required. So in which case, for example, the darios that could have a constant airfoil, or the H rotors can have a constant airfoil from beginning to end, so you can actually do mass production with ease. So a wind farm requires less space for operation than HOT. So in the last page, we are going to see an analysis of how this rings true. Number 5, a HOT impacts heavily on the visual landscape. So yes, you see the effect of the wind turbine system. There's also this understanding that vertical axis wind turbines affect birds less than horizontal axis wind turbines. Then an array of counter-rotating vertical axis wind turbines allows the use of a configuration that has been identified that yields twice as much power per acre as with a HOT. Again, in the last page of this presentation, we are going to look at how it's possible to have more power per meter square or acre for a vertical axis wind turbine than for a horizontal axis wind turbine. Aside that, there are various modifications of the orientation of vertical axis wind turbines that ensure that more wind, the effect of more wind is generated on top of the wind turbine systems. So some are not self-starting, in which case you have to put a mechanism or a component that is going to rotate the blades initially before the wind in the environment takes over the rotation of the wind turbine system. So there's fatigue of blades, because in most cases these wind turbine systems will be running even at wind speed that are not rated. So there could be some form of resonance, which is why there are certain configurations of wind blades for vertical axis wind turbines that are being developed. Aside that, for fatigue of blades, material design could be a way to combat this. So typical materials that are used for VAWTs is aluminium as well as composites. So airfoils and blade cross sections for VAWTs. So for the servonials, they are usually probably a material with a thickness. The cross section could be a regular, for example, a half cylinder, but having a thickness that is resilient against the effects of the environment and the forces on it. So you have elliptical or parabolic cross section of the blade, S-shaped or helical/spiral blades. So these are all the drag driven types. For the darios, which is a lift driven type, you have for heights below 10 meters, you have the NACA 0012 and the likes. For heights above 10 meters, you have NACA 0025 and other DU series of airfoils that can be used for the blades. So characteristic dimension for a 500 kilowatts VAWT and HOT. So for a vertical axis wind turbine for 500 kilowatts, we have 35 meters height and the diameter of 22 meters. For a horizontal axis wind turbine for the same capacity, you have a hub height of 45 meters and a diameter of 44 meters. The difference between them is that for the vertical axis wind turbine, you have most of the blades coming close to the ground surface, but for the horizontal axis wind turbine, only the radius of the blade goes below the hub height, so at least you have some clearance on the ground. So whatever this could, of what value this could be in relation to footprint for wind power system, can always be modeled to understand it better. So performance comparison in a wind farm between a VAWT and a HOT. So configuration for a vertical axis wind turbine, typically you are talking about for that 500 kilowatt wind turbine system that I just identified with those dimensions. For a VAWT, you typically be talking about a distance of 2D, which is the diameter of the wind turbine system. 2D as the distance. So we are not really considering whether it's crosswind or downwind, or we are rearranging the orientation of the wind turbines. We are not considering, it's just basically what controls the distance. So we are talking of 2D, which is about 44 meters between wind turbines. But for horizontal axis wind turbine, you need a minimum of 5D, and the diameter in this case is about 44 meters. So you are talking of 220 meter distance between each wind turbine in the wind direction and in the crosswind direction. So you see how you need more land area in order to generate similar amount of power for horizontal axis wind turbines compared to vertical axis wind turbine system. So we can see that a VAWT wind farm can produce more than 2 times the power generated by a hot farm. Hence, a financial model will put to rest all debates as to whether VAWT should be adopted and mass produced, that is vertical axis wind turbine, whether they should be adopted and mass produced for usage. But so far, they have shown promise. And with the present day technology of material science, in which case you can design for fatigue, and with the level of software that we have, you should be able to design for fatigue and get your stress values. And with material science, you are able to formulate or design a kind of material and test those materials for required performance. So I believe that VAWTs have a chance in the wind power industry for them to begin to be adopted for various projects. Thank you for watching this video. This is Catchment of Resources, where we create for better living.